Assalamualaikum and good day all. In this video, I will show you how to design simply supported rectangular beam. A rectangular reinforced concrete beam is simply supported by two masonry walls with thickness of 250 mm and 8 meter apart. So this is the clear distance between support. The beam has to carry a distributed permanent action of 15 kN per meter, excluding beam self-weight and variable action of 10 kN meter. The material to be used is grade C20 concrete and grade 500 reinforcement. The beam is inside building which subjected to 1 hour fire resistance and designed for 50-year design life. Design the beam. This is data gathered from the question. Effective span is measured from middle support to the middle support. The question gave 8 meter clear distance. For that, we have to add half of the weight of two support. That's what we get 8.25 meter. GK in QK is given. Design life for normal building is 50 years. Fire resistant 1 hour is R60. Exposure class XC1 represent exposure class for structure element inside building. Material strength for concrete, steel and link also provided. Reinforced concrete has a unit weight of 25 kN per meter cube. It is important here we make assumption for our bar. The bar required are bar 1, this is for the tension reinforcement, we use 20 mm. For bar 2, this is for compression reinforcement, we use 12 mm. And for link diameter is 8 mm. First, we have to determine our beam cross-section parameter, which is B and H. We determine our overall depth or height of beam using ratio L/13. For that, we get 635 mm. From estimated H, we determine our B using 0.4 H. For that, we get 254. To round up the value of B and H, we get 250 times 650. It is important to check the B we choose against B minimum for fire resistance. By referring to table 5.5, B minimum is 120 mm. So estimated B is past the B minimum. Now we calculate our concrete cover or C norm. Minimum cover with regards to bond C minimum B is 20 mm. This value is taken from the maximum bar size used in the design, which is tension reinforcement. For min cover with regard to durability C minimum dur, we get 15 mm by referring to table 4.4 and Eurocode 2. For minimum required exist distance for R60 fire resistant, we have to calculate our ASD. The formula for ASD is A plus 10. The value of 10 is taken from table 5.5. A is depends on the nearest B for our beam. Our B is 250 mm, so we should refer to B minimum 200 mm to get our A, which is 30 mm. Therefore, our C minimum due to the fire is 20 mm. Our C deviation is 10 mm. When we calculate our C nominal, the formula is C minimum plus C deviation. Remember that C minimum is taken by the maximum value of C minimum B, C minimum durability, and C minimum due to the fire resistance. In here, the value maximum is 22 mm. We add with 10 mm, so we get our cover 32 mm. On site, it's quite hard to get 2 mm precision, so we round up become 35 mm. Therefore, our cover is 35 mm. Now we do the loading and analysis for simply supported beam. First, we calculate beam self-weight. So this is B 250 and H 650. So we times with the density of reinforced concrete 25. We get 4.06 kilonewton meter. The GK given in the question is 15 kilonewton meter. So we add 15 with the beam self-weight. We obtain 19.06 kilonewton meter. QK also given 10 kilonewton per meter. For the design action WD, we use 1.35 GK plus 1.5 QK. Therefore, we get 40.73 kilonewton meter for our 6 meter beam. We draw the shear force and bending moment diagram and obtain the maximum shear and maximum bending moment. In here, our maximum shear force is 168 and our bending moment is 346.6 kilonewton meter. Now we calculate our D and D prime. D is the distance from the outer concrete to the tension reinforcement, middle of the tension reinforcement, and D prime is from the outer concrete to the middle of compression reinforcement. In here, since the beam is assumed to be arranged like this, our D is calculated as H minus C nominal minus length minus 1 bar. It becomes 587 millimeter. For D prime, it is equal to cover plus length plus half of bar diameter. It becomes 49 millimeter. Our design bending moment obtained from the bending moment diagram is 346.6 kilonewton meter. Formula to get K is equal to M divided BD to the power of 2 times FCK. We have to compare our K with our value of K balance. This comparison will determine whether our beam is singly or doubly. Our K calculated is 0.201, okay, and our K balance is 0.167. Since our K more than K balance means that our beam has to be designed as doubly reinforced beam. For doubly reinforced beam, compression reinforcement is required. You can ignore this calculation for K balance, okay, since we actually know the value of K balance is 0.167. Now we calculate our Z, okay. So our Z is 0.82D, okay, and the for 0.82D is 481.8 millimeter. We calculate our X, okay. The X is 263.1 millimeter. Since it is a doubly reinforced beam, we should check our D prime over X and make sure that the value is less than 0.38 to assume that the compression steel have yielded. From there, we can calculate our area of compression reinforcement using AS prime equal to K minus K balance FCK BD to the power of 2 divided by 0.87 FYK D minus D prime. So our area of compression reinforcement is 252 millimeter square. Now we can use this formula to calculate our area of tension steel. We get our area of tension steel is 1624 millimeter square. Now we have both area, compression and reinforcement. Then we can refer to table 1 to get how many bar we required for the beam. For this beam, we required 3H12, and for the tension reinforcement, we required 6H20. We get both area, we have to check the minimum and maximum area reinforcement using AS minimum and AS maximum. For AS minimum, the formula is 0.26 FCTM. This is tensile strength for the concrete divided by FYK B times D. Okay, and this formula should be more than 0.013 B times D. Since we get our AS minimum as 0.0011 BD, we cannot use this formula. We should use this limit formula. We get AS minimum is 191 millimeter square. Our AS maximum is 0.04 B times H. We get 6,500 millimeter square. So we compare those two areas by the minimum and maximum area for the beam. So it is satisfied, the value. This value is within the minimum and maximum area of reinforcement. Now we look on how to design our shear link. We obtain our maximum shear force for our simply supported beam is 168 kilonewton. We calculate VRD max using angle 22 and 45 degree. We get VRD max 338 kilonewton for angle 22 degree and cotangent theta is 2.5. Another value is 486 kilonewton for angle 45 degree with cotangent 45 is 1. We compare our VED design with our VRD max cotangent theta 2.5 and cotangent theta 1. Since our VED design less than VRD max, mean our angle is less than 22 degree. We now calculate the exact angle using this formula. We get 10.1 degree. Since the range of angle for shear crack is in between 22 to 45 degree, for this case, we no need to use 10.1. We can use angle 22 degree where cotangent 22 degree is 2.5. We use this formula to get the ratio of ASW over S. ASW is the area of shear link and S is the spacing. We get the ratio is 0.297. Since we use the link diameter of 8 mm, our ASW is 101. This is for two-leg link. You can refer to shear link design in previous chapters. From ASW over S, we get our spacing 339. We compare our spacing with the maximum spacing using 0.75D, we get 440. This is the limit, so 339 spacing is okay. On site, to arrange the link at 339 is difficult. We can use 3 to 5. We also can use H8330 or 340 as long as it not go beyond S max. We calculate the minimum link using this formula and we get the ratio of 0.179 or 0.18. We calculate our spacing using this ratio, we get 562 mm. This value is more than S max, so we should use the limit of 440 or less. For this, we use H8425. Then we calculate the shear resistance for our minimum link. Using this formula, we get 134 kilonewton. Our link will have two spacing, maximum and minimum spacing. We know our maximum shear occur at the support where the value is 168 kilonewton. For this, our spacing is 325. The value of shear force reduces as it reaches midspan of the beam. That's why we calculate minimum link. Our minimum link is 425 mm. Since the beam is symmetrical, the arrangement for the link will be the same for the right side of the beam. Here you see, for link near the support, we have the spacing close to each other. But at the middle of the beam, we increase the spacing because the shear is not critical in the middle beam. We use the ratio technique to get what is the distance we require to arrange for the link, maximum and minimum. We know the force for maximum and minimum is 168 and 134 kilonewton. And we also know half of the beam effective length is 4.12 meter. Half beam effective length is 4.12 meter, having the maximum shear force of 168 kilonewton. The distance x from the support having 134 kilonewton. Therefore, the value of x is 0.83 meter. This means we should provide 325 millimeter at 0.83 meter from the support for spacing 325 millimeter. For the minimum link, we deduct the effective length with both 0.83, we get 6.58 meter. For length of 6.58 meter, we arrange the link at the spacing 425 millimeter. We calculate additional longitudinal reinforcement due to the shear link using this formula. We get 208 kilonewton. Then we compare with the moment design divided by Z. We get 719 kilonewton. This value is more than FTD. We calculate what is the AS for the additional longitudinal reinforcement using FTD divided by 0.x7 FYK, we get 478 millimeter square. For this area, we provide 2H20. This 2H20 is already being covered when we provide the area for tension reinforcement. We check the deflection for the beam. We calculate first the percentage of required tension reinforcement. This is the area of tension required divided by B times D. We get 0.011. This is the reinforcement ratio. So FCK times 10 to the power of negative 3, we get 0.0045. Next is rho prime, which is compression reinforcement required area divided by B times T, we get 0.002. This is the simply supported, so our K is 1. We compare our rho with the rho O. Our rho is more than rho O, so we use the equation 2. The equation 2 from the Eurocode. Okay. So we key in all the information, we get our L over D is 14.4. This is the L over D basic. We have to do the modification factor for span greater than 7 meter. Our beam is 8 meter, so we have to have the modification for span. So 7 divided by length is 0.85. Then modification factor for steel area reinforcement is AS provided divided by AS required, and this value should be less than 1.5. So we get our modification factor for steel area is 1.16. Therefore, our allowable span effective ratio is, this is our L over D basic, 14.4 times modification factor for span 0.85 and modification factor for steel area 1.16. We get 14.2. Our actual span effective ratio is length divided by D. We get 14.1. We compare our actual span effective depth with the allowable span effective depth. So the actual is less than allowable. So it means that our deflection is okay. Now we verify cracking on beam. For XC1, limit crack width is 0.3 mm. We'll calculate the steel stress using this formula. This lambda is modification factor for moment. We don't do any modification for moment, so our lambda value is 1. When we get our steel stress, we can refer to table 7.3n to get maximum allowable bar spacing. We then compare with our bar spacing. In this solution, bar spacing is calculated from the middle bar to the other middle bar. We also can calculate spacing from end bar to the other end bar. Since our bar spacing is less than maximum allowable spacing, means our crack is verified. This is last part of our design process, which is detailing. Detailing should have a beam cross-section with reinforcing bars. The view of whole length of the beam with top, bottom, and link arrangement are also shown. Curtailment for tension bar can be done near the support. Look at the note here on how curtailment is made. We know at the support, the bending is less critical, so we can reduce to 25% from the total tension bar area at the midspan. We calculate the reduction and obtain 397 millimeters square. We have to add area of steel for longitudinal shear, which is 478 millimeters square. Therefore, the total AS required near the support is 397 plus 478. It becomes 875 millimeters square. So 875 millimeters square is equivalent to the 3 bar at size 20 and the AS provided is 943 millimeter square. That's why if you look here at the mid span we have 6 bar and towards the end span we have only 3 bars.